Hello friends, today we are discussing about Andrews experiment. Andrews performed a number of experiments to study the behavior of real gases at various pressures and temperatures. Andrews experiments provided detailed and better understanding of the behavior of gases. On the basis of these studies, Van der Waals introduced the corrected gas equation known as Van der Waals equation. In 1869, Andrews performed experiments on carbon dioxide and studied the isothermals of carbon dioxide gas. He obtained the values of volume V corresponding to vapor's pressure, various pressures, keeping the temperature constant. Then he draw the curves of between P and V at constant temperatures are called as isothermal curves. The isothermal curves obtained by Andrews between 10 degrees centigrade and 50 degrees centigrade. So today we discuss the Andrews experiment on the isothermal of CO2. This is the simple structure of experimental procedure. Here the apparatus consists of two similar glass tubes A and B having a thick capillary tubes at the top and the bulbs in the middle. Initially, in a tube A, a pure dry air is passed for a long time and then sealed at both ends. Similarly, in B tube, the carbon dioxide is passed for a long time, nearly 24 hours, and both the ends are sealed. The lower ends of both the tube are immersed in mercury. A small pellet of mercury is drawn in both the tubes by alternatively heat and cooling the tubes. Both the tubes are fixed in H copper vessel, H copper shaped vessel. So this is the H copper vessel having the steel stopper S and S dash. Here the two stoppers S and S dash. The vessel is fitted with water and here is the screw. By screwing in the plunger, the water is compressed and the pressure is transferred or the transmitted to the enclosed gases. The pressure of the order of 400 atmosphere can thus be applied. Since the pressure of air in A and carbon dioxide in B are the same from the volume of air in A, the pressure of carbon dioxide can be calculated. And assuming air to be obey Boyle's law, the volume of carbon dioxide is read from the tube B as it is calibrated to read the volume directly. Both the tubes are surrounded by water baths. Air is kept at constant temperature. The temperature of carbon dioxide could be maintained at any desired temperature between 0 degrees centigrade to 100 degrees centigrade. In Andrew's experiment, isothermals were drawn at temperatures 31.1 degrees centigrade, 21.5 degrees centigrade, 30.98 degrees centigrade, 31.1 degrees centigrade, 32.5 degrees centigrade, 35.5 degrees centigrade, and 48.1 degrees centigrade. So this is the variation of temperature and what is the behavior of gas were studied by the Andrews experiment. So for this purpose, he draw the isothermals of the P versus V. At the x-axis there is a volume, that is the specific value volume, and at the y-axis there is a pressure measured in atmospheres. So here we are considering the isothermal curve, first isothermal curve at 31.1 degrees centigrade. So this value is the 31.1 degrees centigrade. In the portion the curve here from I to J, as the pressure of the gas increased, its volume decreases approximately in accordance with the Boyle's law. In the region of Ij or before Ij, here suppose we are taking the A point, A to I, a carbon dioxide is in the gaseous state. At point I here, nearly 49 atmosphere pressure, the volume of gas or the volume of mass is very small, and further increase in a pressure causes the mass to liquefy. So in this state I to J, the gas should be, carbon dioxide should be liquefied. This mass is said to be a saturated state in the sense that there is no more matter can exist in the gaseous state in the given volume. A slight decrease in the volume causes saturated vapor to condense into liquid. A further decrease in volume results in continued liquefaction of the mass, and the pressure is almost remains constant. So this line representing the pressure as we are decreasing the volume. So this pressure remains almost constant. This is represented by the horizontal portion, that is curve Ij. At point J, the entire mass is converted into liquid. The portion Ij represents the equilibrium between liquid and vapor phases. If the pressure is further increased here, the volume almost remains constant. As the liquids are almost incompressible, this is represented by portion J to this line. This is the of the isothermal of the curve. Now the curve we are taking, the volume, the temperature is going to increase from 31.1 degrees centigrade to 21.5 degrees centigrade. So this is the pink color shade, from starting from point A to B, B to C, C to D. So this black line are representing the gas phase, while this black line is representing the liquid phase. Now what the curve curve A, B, C, D at 21.5 degrees centigrade is similar one to the 31.1 degrees centigrade, the AI, J, D. But the horizontal stretch here, the line is the larger than this line. So this C to B line is smaller, stretched, indicating that the difference between the volume, saturated vapors and the liquid is not very large. In this case, the saturation point at B is obtained at higher pressure compared to this value I. But at 31.1 degrees centigrade, that suggests that a larger pressure is required to liquefy the gas or vapors at higher temperatures. The horizontal spread of the curve goes on decreasing. यहाँ पे कितना है उसका J and I का line ज़्यादा है. So the liquid and gaseous phase का state कितना है यहाँ पे 31.1 डिग्री सेंटीग्रेड पे वो ज़्यादा है, हॉरिजॉन्टल लाइन ज़्यादा दिखाई दे रही है. वही यहाँ पे कितना हो रहा है 21.5 डिग्री सेंटीग्रेड पे वो कम हो गया. तो ये कैसे क्यों कम हो गया? बिकॉज यहाँ पे जो लिक्विफाई गैसेस टू लिक्विडफाई का प्रोसेस होने का स्टेट है वो कम है. दैट रिप्रेजेंटिंग द डिक्रीजिंग विथ राइज इन टेम्परेचर. यहाँ पे अब नेक्स्ट स्टेज क्या होता है कि एट 30.98 डिग्री सेंटीग्रेड यहाँ पे टेम्परेचर कांस्टेंट किया है उसने. कितना किया? पहले किया था 31.1 डिग्री सेंटीग्रेड पे. यहाँ पे उसका फेज देखा उसने कितना होता है, लिक्विड एंड गैसियस फेज का ये स्टेट होता है. बाद में वो एंड्रयूज ने टेम्परेचर इंक्रीज किया 21 डिग्री सेंटीग्रेड और वो कांस्टेंट रखा है. तो वहाँ से ये स्टेट मिला हमें. कौन सा? A to B, B to C, C to D. A to B क्या इसमें क्या हो गया है आपका, ये डिक्रीज कर रहा है, अब वॉल्यूम डिक्रीज हो जा रहा है उसको क्योंकि तो कंप्रेशन ज़्यादा आ रहा है, डिक्रीज हो गया. तो यहाँ पे भी फ्लैट पोर्शन आया, बट ये फ्लैट पोर्शन इस कंपेरेटिव कम है. यहाँ पे लिक्विड एंड फेज गैसियस फेज का पोर्शन जो है वो कम होता है. मतलब एक स्टेट से दूसरे स्टेट जाने के लिए उसको ड्यूरेशन कम लगता है. अब at 30.98 what happens? Again the points are increasing here as volume going to decrease, and the atmospheric pressure is almost 73. Okay, and here a small flat portion is appearing on this point, and later on suddenly the state will be changed, so liquid phase is there. But beyond this temperature, what action takes place? That is the 31.1 degrees centigrade. The horizontal spread curves on decreasing with rise in temperature. At this point, it almost vanishes. This shows that gas is not liquefied after this here. For this line 31.1 degrees centigrade, there is no liquefaction. The tangent to the curve at point X, this point here we are representing, indicating that the point X, or here simply E point, is horizontal. In fact, point X, point of inflection, and the slope of curve on the two sides of this point are opposite sides. At this stage, dP by dV, change in pressure by change in volume, is equal to 0. This point is called as critical point, and the isothermals on which the point lies is called the critical isothermal. For carbon dioxide isothermals, above the temperature 35.5 or 31.1 degrees centigrade to 48.1 degrees centigrade, the horizontal portion does not appear at all, and the gas obeys Boyle's law. So from this line, from this green to dark red, or beyond this one, it behaves like a ideal gas and obeys the Boyle's law. From one end to other, these isothermals are similar to the isothermal of air. ये यहाँ से इसके ऊपर ये लाइन जो है, ये जो आइसोथर्मल्स है, ये एयर के आइसोथर्मल के हिसाब बराबर दिखते हैं. So it is similar to isothermals of air. Thus for carbon dioxide, the critical isothermals divides into two regions. Above the critical region, or above the critical isothermal, the gas or the carbon dioxide cannot be liquefied. However, large the applied pressure may be, below the critical isothermal, from this line, carbon dioxide gas can be liquefied by the application of pressure alone. The dotted curves, this line, or what we say, the shaded area of this line, gives the liquefaction, or what we say, the liquid and gaseous phase. So this shaded area is represented as a liquid and gaseous phase. Here in this area, the curve whose highest point is P, here what is the highest point is E, is called critical point, and the temperature at 31 degrees centigrade isothermal is called the critical temperature. This pressure, volume and temperature corresponds the critical values. So from these isothermals, here these shade lines or this area is referred as the gas phases. Here the carbon dioxide in gas phase, while this dotted area, or what we see the shaded area, is the carbon dioxide in liquid and gaseous phase, while this pink area is liquid phase, carbon dioxide in liquid phase. At point E, there is no change, so this temperature, no change means there is no liquefaction process, direct this phase converted into, or it behaves like a air. So gaseous phase, the carbon dioxide behaves like a isothermal of air. So this temperature is called as critical temperature. So critical temperature of carbon dioxide is 31.1 degrees centigrade. Then at critical volume, what action takes place? So यहाँ पे वॉल्यूम कितना है, इसका कंप्रेशन नहीं है, so it is compared to air, so this is the critical volume. And at this pressure, what is the, that is the critical pressure. So all these are, and this point is called as a critical point. So what happens with the critical constant? All these are the critical constants of a given gas. Above the critical temperature, the liquid state is not obtained. Thus it is concluded that the above critical temperature is not possible to liquefy the gas by applying any large amount of pressure. The isothermal at critical temperature, that is 31.1 degree or 31.4 degrees centigrade of the carbon dioxides, indicates that on increasing the pressure, the volume of the masses decreases very fast, much faster than that predicted by Boyle's law. On joining the extremities of the horizontal portion of the isothermal curves, we obtain almost a parabolic region on the P and V graph. In this isothermal, the shaded area gives the apex of these curves touches the critical point here. So this curve shaded area of apex touches to the critical point. The region below this parabolic region represents the equilibrium of vapors and liquid states here of the substance. To the right of the parabolic region, the curve represents gas phase here, or vapor phase, while left represent liquid phase, this one. The region above the critical isothermals curve represent the gaseous state. Above the critical temperatures such as 32.5 degrees centigrade, the isothermals through exhibit a nick but never show a horizontal region. यहाँ से this shows that the compressibility of the gaseous mass is extraordinarily high. Initially, the rate of decrease of volume with increase of pressure is high, which decreases in the neighborhood of critical point. At high temperature, even this tendency vanishes and the gas starts obeying Boyle's law from this region. The kink in the curve decreases with increase in temperature. Above 41.1 degrees centigrade, it totally vanishes, and this isothermal becomes almost hyperbolic as predicted by Boyle's law. Thus at high temperature, carbon dioxide behaves like other gases such as oxygen, nitrogen, etc. So above 48 point degree centigrade, carbon dioxide behaves like a air, or it obeys the Boyle's law. So this is the Andrews experiment, and were performed with number of temperature constant by changing volume and pressure, and studied the behavior of gas. So we can define now these critical points: critical pressure, critical temperature, critical volume of the carbon dioxide or any gases. So first, critical temperature. It represents as a Tc. It is defined as the maximum temperature at which a gas can be liquefied by the increase of pressure alone. Above this temperature, the gas cannot be liquefied, however large the applied pressure may be. The next, critical pressure. What is the critical pressure? The pressure is necessary to liquefy a gas at a critical temperature is called critical pressure. The third is critical volume. It is the volume which unit mass of gas occupies at the critical temperature and critical pressure. So these 3 points or quantities like Tc, Tp and Tv. Tc stands for critical temperature, Pc stands for critical pressure, and Vc stands for critical volume, are called critical constant of gas. So at this point there is a critical point. So it is that point on the isothermal for the critical temperature at which the change of state from the gaseous state to the liquid state takes place under constant values of Pc and Vc. So this is the Andrews experiment and critical temperature, critical pressure, critical volume and critical point. One term is there, that is the state of continuity. Andrews isothermal curves also indicate a continuity between the liquid and the gaseous states. In the isothermal, above the critical point, carbon dioxide is in gaseous state. Below the critical temperature, it is in the liquid and vapor state combined. And on the curve where the carbon dioxide is in vapor state, while at the point on the same the value, just I will show this region where the carbon dioxide is in gaseous state below the critical temperature. So go to the first slide. Here, so this region where we are indicating, यहाँ से ये line और यहाँ से this line representing the liquid and vapor states combined, and it is in the liquid state. So that from D point, suppose here from D point to this point, so this phase, what we say, यहाँ से लेके यहाँ तक का ये liquid state का phase. If we follow the curve from यहाँ से लेके यहाँ तक का, from the point this to this, यहाँ तक का, start liquefying and continuity of the state is destroyed. यहाँ पे the curve becomes discontinuous, but if the keeping the volume fixed, we go on increasing the pressure up to point, just we are increasing the pressure, then the keeping the pressure constant and decreasing the volume, we can obtain the state corresponding to this point G point के लिए, G to F के लिए. In such a change, both the liquid and vapors, both states are not obtained simultaneously. Such change maintains a continuity between the liquid and vapor state. The two conclusions from the Andrews studies. Any gas can be liquefied below its critical temperature. Means the critical temperature of carbon dioxide, oxygen, nitrogen, hydrogen are at 31.1 degrees centigrade, minus 118.8 degrees centigrade, minus 147.1 degrees centigrade, and minus 239.9 degrees centigrade respectively. See, means for the carbon dioxide it is 31.1 degrees centigrade. For the oxygen it is minus 118.8 degrees centigrade. For the nitrogen it is minus 147.1 degrees centigrade, and for hydrogen it is minus 239.9 degree centigrade. Then above the critical temperature, the gas cannot be liquefied by applying any laws or any large amount of pressure. Then at the critical temperature, the density of the liquid and its saturated vapors becomes equal. At this temperature, it is not possible to differentiate between the two. In the neighborhood of the critical point, the compressibility of the gas is very high and it becomes infinity at the critical point. Above the critical temperature of the behavior of the gas mass is similar to that of so-called permanent gases. There is continuity between the liquid and gaseous state of the matter. So these are the conclusion of Andrews studies. So this Andrews experiment studied the behavior of gases. In this session, in this article, we are studying the behavior of isothermal of gas, of carbon dioxide gas. So thank you very much for watching this video.